Okay, class, I'm going to show you guys a video from Worksheet 3. Okay. In Worksheet 3, I'm going to do number 1 for you. After I do number 1, you should hopefully be able to do the rest of the problems. Okay. Worksheet 1 is maybe one of the longest, so let me get my chair. Okay. So, I showed you guys in the previous video how do I solve my word problems, and so we're going to use those same steps to help me help us figure out how to solve this one. All right. So it says a race car has a mass of 710 kilograms. It starts from rest and travels 40 meters in 3 seconds. The car is uniformly accelerating in this entire time. Friction and the drag force combine for a total of 1,189 newtons of resistance force. So we can just say the drag force or the friction force, whatever. We can go with whichever one we want as long as it's a resistance force. Okay. It says how big is the net force. Okay, we'll figure out what that means. And make a quantitative force diagram. Alright. And it says how large is the forward traction force acting on the car. This is a rather interesting question, right? Because the first one, let me actually list what we're given first, because that helps me set up my problems every time. Alright. We're given the mass of the car. The mass of the car was 710 kilograms. It's stated in the problem that it's 710 kilograms. Okay. It says that it starts from rest. So if it starts from rest, I'm going to put that my initial velocity was 0 meters per second. It says it travels 40 meters. So the meters is an indication that it's a displacement of 40 meters. And it does that within 3 seconds. Okay. Cool. Awesome. Fantastic. We are really getting somewhere because look, we have a lot of stuff written on our paper already. Now, next. It says how big is the net force? Well, how do I figure out net force? Well, this is one equation you guys need to know for the entire unit. Is from our lab we got the acceleration is equivalent to the sum of our forces divided by our mass, right? This symbol right here, when we have the sum of our forces, that is the same thing as calling it net force. So our net force is the same thing as the sum of our forces. Okay. That is important to keep note, is the sum of the forces is the same thing as saying net force. Alright, it's the same thing. So it's asking us for this guy, right? So what that means is I'm gonna come over here and I'm gonna rewrite it, but I'm gonna write it like this. How did I get this one down here? Is I multiplied both sides by the mass. So I multiplied this whole thing by m. I get just the sum of forces, but I have to multiply the other side by m, and so I get this guy. So, in order to get the net force for part A, I need my mass and my acceleration. So because I need those two, I'm going to come over here and look at what I got, and I say, oh, I have my mass, but I do not have my acceleration. But what I do have is I do have my initial velocity, the time, and the displacement. So I'm going to want to find the acceleration also. So let's do that. So what I'm going to do is I'm going to come up here and I'm going to copy down my conditions. I'm going to copy down what I was given. I'm just doing this for space. Okay. So, this is what we're given and what I'm finding at the moment. Okay. How did I come to deciding that I need to find acceleration? It's because down here I need acceleration for my net force. Alright, so I come over here and I say, cool, I have all this information. Then I look at my formulas, I look at my equations, I say, okay, which one has to do with acceleration? Well, all three of them. Okay, that doesn't help too much. I have time, so which one doesn't have to do with time? This one does not have to do with time, so we can ignore that one. So it's either this one or that one. Which one has to do with initial velocity? Both of these two have to do with the initial velocity, right? And then I look and say which one has to do with the displacement. This one does, the other one doesn't. So this one is the one that we need. Okay? So I'm going to write down the equation I need. Okay? The equations will be given to you at the top of the tests, so the equations will be given to you on the test. Okay? So now I'm going to plug things in. So delta x is 40. Okay. The initial velocity is 0, right? The time is 3 plus 1/2 the acceleration multiplied by, and again the time is 3. Don't forget the squared. Okay. We can ignore this guy because 0 times 3 is 0, right? So we get 40 equals 1/2 multiplied by acceleration multiplied by 9. If I do 1/2 multiplied by 9, we get 4.5. And then if I look at my stuff, because I did this beforehand, if I look at it, and if I plug it in, because we need to divide both sides by 4.5, so the acceleration is 40 divided by 4.5, so the acceleration is equivalent to I didn't put an actual number. Well, let me get you an actual number. I kept it as a fraction on mine. I get 8.88888, and then so I'm going to cut it off right there. Okay. Cool. I want to use this number again. So on a calculator like this, one of these graphing calculators, if you have one, there's a little function on them called store as a variable down here. You can press that. And then I always wondered, why is there the green alpha in the letters? Well, you can store it as a letter. So right there it says I stored it as variable A. So for some of you who have these calculators, every time you type in A into your calculator, it uses that. So it's a nice little function that I was never taught. Alright. Now, back to our problem. It asks for the net force, which has to do with the mass multiplied by the acceleration. And so we just found the acceleration, and we had our mass of 710 kilograms. So I always write down the formula just before I plug things in. And so I put it into my calculator. I get my net force to be 6,311.11 newtons. Now, some of you might, simply use this into your calculator. That's fine. Personally, I have my own personal preference where I like to keep things in the calculator, and I use what's in the calculator. So I use my previous calculations, and so I use the full number. That's just my preference of what I usually do. So, part B, it asks us draw the diagram. I apologize for this being long, but it's better than nothing. Alright, so that's my car. Let me put this above, so that's my car. Now, on any object on the earth, there's always a gravitational force on the object, right? I'm just gonna be lazy and not do the full labels. Since our car is 710 kilograms, what you guys need to remember is the gravitational force is our mass times our free fall acceleration, or it's mass times the gravitational field strength. And so you do 710 kilograms multiplied by 10 newtons per kilogram, or same thing as if you did 10 meters per second squared. It's the same thing. And so we get the gravitational force to be 7,100 newtons. Now if I were to say there's a normal force on the car, we're assuming it's on a flat surface, so I get that. The reason I say that the normal force is the same thing as the gravitational force. Oh, wait. I'm not drawing things the same way that black did. I'll fix that later. I'll fix that. The reason I'm saying these two are the same is because we're on a flat surface, and because we're on a flat surface, then our car is not falling into the ground. Because if the car was sinking into the ground, that would mean that the gravitational force is larger than the normal force. And if the normal force was larger than the gravitational force, then the ground would basically like reject the car, and so the car would be like being kicked off the ground somehow, which is nonsense. There's a frictional force going this way, and they gave it to us at the beginning of the problem, 1,189 newtons. And they hinted that there's something called like a traction force in the problem. They say, how large is the traction force, quote unquote. Just call this the force applied for now. Make it your life simpler. Alright. The force applied by the car. That way, so it's easier to understand. So we have all that. That's nice. That's dandy. So let's kind of draw it the way you guys were taught. I apologize. Okay. Now, let me get my chair so I can sit and talk. So, sorry about the down shot. Alright, so, I drew this. Now let me explain why I drew it so that you guys can sink it in just a little bit more. Alright? I drew the normal force and the gravitational force. I drew those two be the same length because, again, when you have a car and you draw your thing on it, your car is not sinking into the ground, nor is the ground like rejecting it, you know. And you know, so the forces in that direction need to be equivalent to each other. Now, why would I draw the applied force by the car, or the traction force? I'm kind of like doing the traction force of the car on to be larger than the friction force? Well, it says that the car accelerates uniformly. It says there's an acceleration, so that means that the car moves. Okay, well, okay. It accelerates, it changes its velocity. That's what I need to say. It changes its velocity. So because there's a change in velocity, there's an acceleration, and so these two forces are not going to be equivalent to each other, because when we have something going at a constant velocity, they are equivalent, but when something's not going at a constant velocity, they are not equivalent. Okay? I hope that drives home that when an object is not going under constant velocity, they are different lengths. And so this force has to be bigger than this force in order to push our car forward so it can move. Okay? So what I'm going to draw is a net force vector right there. It looks a little bit weird, but if I were to single this guy out and we look at him real quick, or her, or whatever you prefer, our acceleration vector, our vector for a force pushing it forward is large, right? It's going larger than the frictional force, so the object is going to go that way, which is why I drew my sum of force vector going in the same direction as my larger force. Okay? And this vector is usually drawn in the direction of the acceleration. Okay? We usually use that vector to draw the direction of the acceleration of our object. Okay? That way, so we know where our object is going. So let me finish my labeling. Okay, and then this right here was, we got 6,311.11. Okay, so we get that. Now, when we do this, we say this side is equivalent to that side, right? Well, the length, I can't get my fingers. The length of this guy is the same thing as the length of those two little vectors added together. You can see that, yeah? Length of that, same thing as the length of that. Length of that, same thing as the length of that. So, what I'm gonna do is I'm gonna say that my, whoa, that's sloppy. That my applied force, or my traction force, whatever you want to call it, is equivalent to my sum of the forces plus my frictional force, because again, this right here is the same length as that right there. Okay? So my applied force is my 6,000 at 0.11 plus 1189, and we happen to get that. That's a little sloppy again. Okay. That's sloppy. Goodness. Okay. So, we got that our traction force, we got it to be 7,500. And if you want, you can include that. Okay. We have our diagram now fully labeled. I'm gonna go over what we did to solve the problem one more time. Just for a reiteration, because my students say that it helps them when they say again the process that we went through in order to solve our problem. Okay? So, first things first. You read the problem. You read what it has in there. You say, alright, we have our race car, it has the mass, it has all this fun information. Alright? I'm not going to repeat everything step by step, I'm just going to go over what steps we took. Alright? After reading the question, even before I even try and solve anything, I write down what I'm given. I do realize that I did forget to write down that the friction force was 1,000, or yes, 1,189. I should have written it down there, but I forgot to. Okay. All right. So after doing that, then what I did is I said, okay, what is it asking me to find? It's asking me to find the net force in part A. And when we're talking about net force, we're just saying the sum of the forces. So what we did is we used the equation we got from the lab, okay? We readjusted it so we can find net force. We have our mass because it gives us our mass, but we do not have our acceleration. But we can find our acceleration based off of the information that we have been given so far. So what we did next is we went over here and we said, all right, let's look at what we got. We have all this we have the displacement, initial velocity, time. We're finding acceleration. We selected the equation out of our set of equations. I do realize we're missing one, but it's one that we don't use that often. But besides the fact that we selected the equation we were going to use, I wrote it down before plugging anything in. Even if it's already on the paper, even if it's on the same whiteboard, even if it's in the same vicinity, I still wrote it down so I knew exactly where to put things place by place, so that I understand so I see where all my numbers are going. I multiplied everything out and I found my acceleration. After I found my acceleration, then I plugged in the numbers that I found for my acceleration, and I plugged in my mass. Alright, because those are what we were given. Then afterwards, then I came down here and I labeled a free body diagram, and then I drew a free vector diagram in the way that Miss Blackwood. Alright. And I showed that the normal force is equivalent to the gravitational force because, again, our car is not going to sink into the ground and the ground is not going to reject it from the ground. That doesn't make sense. I labeled my traction force as I labeled it as an applied force, and I labeled my friction force. And again, because our object is accelerating, we do obtain a situation where before I drew this guy, he was just missing, and then so we just had that, right? And then I included that guy to show, look, this is longer than that, so the acceleration has to go that way. And so I drew my net force vector, and as I said, you draw the vector in the direction of the acceleration. I labeled the numbers on everything, and then I said that this length is the same thing as these two lengths added together. So I wrote that down, and I solved, and then I labeled, and then we were done. I hope this was helpful to you guys. The other problems should follow similarly. If there's any equations that you need that you don't have, let me know, but I do. They are there. They're all there, and you need them all. And I did put up here as a review, yes, the gravitational force, you do need to know how to calculate that by now. Okay? So, that's it for today. And I believe you should be able to finish worksheet 3. Oh, sorry, my camera kind of veered off. My bad.